Okay, well, I hope no one's going to be really disappointed. I'm not going to talk about KIC 119, but I'm going to talk about GD1212 instead, which came up from the Kepler 2 test run. So popped up a few months ago, got better results, so I guess it's more exciting for you. So we didn't talk a lot about white dwarfs, so just a brief recap. We know white dwarfs are the lower end of the HR diagram, right here. That's that strip there. And I'm going to talk more specifically about the ZZ Ceti instability strip. So I'm going to talk about, well, they're known DAV here, that pulsation class. They're hydrogen-rich white dwarfs, and they present G modes. So here we have the instability strip. It's a pure instability strip. So every white dwarf starts pulsating close to the blue edge, and then as you move along, it gets really tricky. We get nonlinear effects, frequency sum and differences peaks that gives us a lot of trouble to identify the mode. Furthermore, we have the pulsation shape vary dramatically with time, so it gets really tricky. So we usually stick to blue edge stars, where was KIC 119. But, so the question is, why GD1212? It's clearly red edge star. Here the circles are a representation of the average periods of the pulsation spectrum, and it's a logarithmic scale. And here it's also placed on the red edge because of the spectroscopic determination. Well, basically, why GD1212? Well, because we had data that came, and they were pretty nice data. And as we move further away from the middle of the strip and we get to the red edge, we see there's kind of the nonlinear effects fade a little bit. So it's simplest of the complicated pulsating white dwarfs, or ZZ white dwarfs. So about the light curve processing. So it was during the Kepler 2 test run. We had 9 days of data. Here you can see the light curve. I want to emphasize here it's the Fourier transform. So here it's a complete Fourier transform, as you can see here. We see two major forests of peaks, and here is the zoom in. We can recognize some kind of pattern, so mainly due to rotational splitting. I'm going to talk more in details about that after. Here we have a regular peak extraction. So here it's the Fourier transform, and here it's the recombined Fourier transform. Here is just a simple subtraction of the two. So I think was a good job done. Out of that, we get a whole bunch of frequencies. Some of them are linear combination up there. We have some more down there. Mainly out of that, we have 13 independent modes that we extracted, which are going to be used for determining the structure of the star. We individualized 19 more components who were coming from rotationally split multiplets. So these are going to help us for the rotation parts. So now the technique. Well, we use the forward method. I'm from Montreal, so I don't know if you guys are familiar with what we do, but we do forward modeling method. So basically, it's a comparison between the observed frequencies and theoretical frequencies from static parameterized models. So here, a brief recap of what a white dwarf looks like. So schematic. So it's basically a thin hydrogen layer on top of a thin helium layer and a carbon-oxygen core. For us, here, we're going to use homogeneous core. So it's a mix of carbon and oxygen here, and it's homogeneous. We know it's not really realistic. Well, we think it's not really realistic, but that's the best we can do so far, and I'll show you why after. So here we have all the parameters that were used to define a static model. So basically we have, well, effective temperature, surface gravity, or mass, as you wish, the fractional mass of hydrogen and helium, and we can add the core composition as a parameter, and these two factors are just a way to represent the transition between the two layers. So they're just a factor, a multiplicative factor to the equilibrium profile at the helium-hydrogen layer and the helium-carbon-oxygen layer. We can also add the convective efficiency as a parameter, But tests have shown that for low radial order, this parameter is not really influenced, does not really influence the modeling. And we tested it, and it's actually the case for GD1212. So we can remove this one and fix it to the prescribed mixing length theory of ML2 and alpha equals 1. Sorry. So more about the technique. So it's a double scheme optimization. So basically, we have one first optimization right here. So we have one model, so defined uniquely by the temperature, log G, etc. And so we define one unique model, and with that unique theoretical model, we've defined one unique frequency spectrum that we get here, and we compared it to the observed frequency spectrum. So we have as many parameters as we want to compare it to. So we just, if we have our 13 parameters, we'll comparing to 13 theoretical frequencies. We obviously had to do an optimization here to find the best mode identification because it's not predefined. So what we give in the model is just the list of the frequencies, but they're not identified. So here we get the identification per uniquely determined per each model. Then we get a second optimization, which is described by the merit function S squared, which is an equivalent of a chi-square, regular chi-square. And we can get a mapping of the projection because we have a parameter space of 7 parameters. And so we can get projections of the different solutions that we can find. And so by looping here with the genetic algorithm, we get an optimal model. So what we get essentially is an optimal model and the identification that goes with it, the best identification. So we get both. So what can we infer from that? Well, obviously, those 4 parameters that I've talked about. It's an independent measure, and we can get extra. So we can get a hint on the bulk core composition and the internal rotation profile. So I'm going to talk first about what we get for our optimal model. So here is the projection on the log GTF plane. So here you can see it's effective temperature against log G. Here in blue, it's our seismic solution. I'm sorry for the typo. Seismic solution here. And the black box is the spectroscopic solution, the 1 sigma spectroscopic solution. So we see we find a solution well in agreement. We have a well-defined solution. And I have to mention that here, it's the color scale is a logarithmic scale. So there's actually a great difference between the blue zone and the red zones. It's emphasized more. So here we have a nice fit so far. If we look into the projection of the hydrogen layer against the helium layer, we found that there are few solutions. Here is our solution, well defined as well. We look like it's it looks like it's a really thin hydrogen layer. But the main question that people usually ask is, but you're doing an homogeneous core and it's not really physical. So we tried with non-homogeneous core. So we took chemical profiles from evolutionary tract, and here you can see one from Salaris et al. 2010. And so you have a distribution for the oxygen and the carbon in the core. And here is the result that we get after the optimization. We see 2 things. First, we have a degradation in the value of the S square by a few orders of magnitude, which is quite huge. Then we can recognize the pattern here. So we can see he's finding the solution, but it's really numerically really noisy. So as we know, the profiles are not that certain, so probably all those little things get the identification more tricky. So even if the homogeneous core is not the best model, it's still a good approximation, and it's at least we get rid of all the numerical uncertainties and all this numerical noise. So now onto the core composition, the bulk core composition. So if we want to look at which part of the star contribute the most to the pulsation, we look at the weight functions. As we know, evolution has pushed the G modes towards the outer layers of the star. So here it's the normalized radius, center of the star, surface, and here the normalized weight function. Here it's a function of the log Q. So it emphasizes more the envelope. So we see mainly that the wave functions are really present in the outermost layers. So we see here the hydrogen layer, the helium layer, and here is the homogeneous core. Here is the same color scheme. But what we can see, we still have here, if we can notice, we can still have a certain sensibility to the core composition. So based on our optimal model, we get roughly the carbon-oxygen of 50-50%. Of course, we cannot take that for granted. So we have to do some other calculations since we're not probing the whole core. So what we find, so what we find here, that's our results. We see we have some kind of Gaussian shape function, which is good. So we know we're not really that wrong. It's really around the 0.5 of the, 50-50% composition. Now if you compare to evolutionary profile, so by doing the same, by doing the inverse of what we're doing, so we're using the weight functions, and by integrating the area under the weight functions for this specific core composition, we find a mix that is pretty, well, yeah, that doesn't add up, but it's pretty convincing that we're actually really testing the bulk core composition. So we're actually most probably having a core composition that has this percentage or this amount of oxygen and carbon, but we need to smooth up a little bit the profile. So the profile needs to be improved so we can get better seismic, so the exercise can be better done. So now if we look at the rotation kernels, we can see that they go deep actually into the interior of the star. The same thing as before, so this is the normalized radius, center of the star, the surface, has normalized rotation kernels. And we see, if we zoom in, we see that the rotation kernels will go quite deep into the interior. So let's see what this gives us. So by using the rotational splitting, so here we see all the multiplets. The pink ones are the L=1 mode, and the green component are the L=2 modes. So these are the two main structure that we could see. You see, this one is a little bit more tricky to figure out than this one, but based on this one, we could refine this one. So based on this, what we can get. By doing, here I'm gonna say it first, we're not doing inversion type exercise. We're just testing if it's a solid body rotation law that governs the star. So basically here we have the period of the core as a function of the radius of the star. So here we have the surface, and here we have the center of the star. A straight line represents a validation that it's solidly rotating. So we see that here it's pretty straight to me, and we are going up to 20% of the radius of the star, and which encompass more than 90% of the mass of the star. So we can actually say that this star is solidly rotating. The period is around 7 hours, which is one of the fastest ZZ Ceti star, but for a white dwarf, it's quite slow if we compare the kinetic energy compared to the total internal thermic energy. So rotation has we can say that rotation has no effect on the evolution. Here are all the multiplets that were used. So the blue are the theoretical, and the red dots are the observed ones. So we can see that it's quite coherent with all the multiplets we can find. How does it compare now to other ZZ Ceti stars? Because usually we do those kind of tests with blue edge stars. So this is R548. So we can see that we're just probing just 5% of the radius, so that tiny bit here, instead of this one. So this star is quite particular because the multiplets we found correspond to the mode that goes actually really deep into the core. So to get a better view of what we're actually probing, we can see that. So we can actually unravel a lot more with GD1212 than blue edge stars. So as a conclusion, the main thing is it works. We have been able to determine for GD1212 the main parameters, the main stellar parameters. But as an extra, we can have hints of how to constrain the bulk core composition And for the first time, we have actually internal rotation profile that goes really deep into the stars. And of course, there's future prospects, so I hope Sandra Grace will help me on that, on finding other white dwarf in the field of Kepler-2. And so there's, yeah, more work to do. Thank you.
Questions for Noemi? Yeah, Aldo.
How strong is the constraint that the spectroscopic gravity puts in the fit? Because the star, it's cool enough that the 3D model atmospheres developed by Tremblay and so on should have an effect on the gravity measured in the spectrum.
Actually, the spectroscopic solution that I put was included the Tremblay's correction, actually, for the high log G problem, right? Is that what you were mentioning? Yes. So it could go between, because here we're right on the high of the bump of the log G problem. So the correction is quite big. So I put the box around 1 sigma, but if I had to include the with or without the correction, that would actually do the whole strip, mainly. So yes, that's an issue.
I have a question, actually. I thought it was an interesting approach to see how your uniform assumption of composition sampled a realistic evolutionary profile. How fine is that search in the carbon-oxygen mixture in your model grids?
It goes to the precision of the machine. But if you do a projection, I don't know if you could see this one, the histogram. Mm-hmm. So we can see the distribution. So that's basically a likelihood functions. And so it's projected. So you get a Gaussian shape. So obviously it's not that number precisely, but we get something around 50-50, I think. We can.
So the search is continuous between 0 and 1?
Oh, yes. Oh, yes. Yeah,
Got
the precision of the machine. So, yeah.
Nice. Other questions? Okay, let's thank her again.